Alright, here we go. Sorry. So I already have myself humiliated up on YouTube right now with this thing not working. So Redemption, here we go. Wait. So it's aimed directly at it. We'll see if this works. Here we go. 3, 2, 1.
A third time.
I don't know if
I have recording.
Did it hit?
I have to record.
It hit the metal? Yeah. Alright, let's try it. Driving me nuts. Whoa! Whoa! Here we go. 3, 2, 1.
It hit the vice.
Why is it curving?
It's human error. Come on.
That's logic. That is shouldn't curve.
No. It would hit the earth. Exactly. See? David, how do you
Alright, one last try then. I'm just It's a quantum effect when you measure it. 3, 2, 1. Alright. Gee whiz. Yeah, I don't trust me anymore. Okay, so
Wait, was it not working?
this time, and I'm gonna have to like double check a couple things, but like
no, this seems like angled. Because like when you put the metal thing down, it's like side.
that shouldn't change anything though, because it's just dropping, you know, like that. Yeah, I think it was more, especially when I saw the ball curve like this. I think I might have I'm kind of careless. I was going to do this, so it might have spun while I don't know. Yeah, and so I'm going to try different ones. I'm interested in this now. This is going to bug me. So, okay. Not to say it wasn't interesting before. I mean, it's a pretty cool calculation and everything that we did. But what I'm going to go over today is actually, we're going to go over chain rule because we're going to use it for the activity that we're going to do later. I will say I'm going to change the homework, so the homework that's due tonight, I might delay. But I have to look at it. So I'm going to look at it, and then I'll figure out whether or not I'm going to delay it. Yes? Do you know chain rule? Yeah. All right. It's right there next to the general. So chain rule. I'm just going to go and I'm just going to show you the Khan Academy video because he does a much better job than I ever could, and I'm probably going to lose my job to automation. So here we go. This guy's just too darn good. If only his physics was better. His physics has issues. What?
Oh yeah.
MrMontrella.com. I don't. 40-minute video. I was about to say that. I'll go with the 5-minute video.
That's what I did.
No, 14. I was thinking of doing that, but I don't. For people who don't know chain rule, I want to.
What we're going to go over in this video is one of the core principles in calculus. And you're going to use it anytime you take the derivative of anything even reasonably complex. And it's called the chain rule. And when you're first exposed to it, it can seem a little daunting and a little bit convoluted. But as you see more and more examples, it'll start to make sense. And hopefully it'll even start to seem a little bit simple and intuitive over time. So let's say that I had a function. Let's say I have a function h of x. And it is equal to, just for example, let's say it's equal to sine of x. Let's say it's equal to sine of x squared. Now I could have written that, I could have written it like this, sine squared of x, but it'll be a little bit clearer using that type of notation. So let me make it. So I have h of x. And what I'm curious about is what is h prime of x? So I want to know h prime of x, which another way of writing it is the derivative of h with respect to x. These are just different notations. And to do this, I'm going to use the chain rule. I'm going to use the chain rule. And the chain rule comes into play anytime your function can be used as a composition of more than one function. And as that might not seem obvious right now, but it will hopefully maybe by the end of this video or the next one. Now what I want to do is a little bit of a thought experiment. A little bit of a thought experiment. If I were to ask you what is the derivative with respect to x, if I were to supply the derivative operator to x squared with respect to x, what do I get? Well, this gives me 2x. We've seen that many times. Now what if I were to take the derivative with respect to a of a squared? Well, it's the exact same thing. I just swapped an a for the x's. This is still going to be equal to 2a. Now I will do something that might be a little bit more bizarre. What if I were to take the derivative with respect to sine of x, with respect to sine of x, of sine of x squared? Well, wherever I had the x's up here, the a's over here, I just replace it with a sine of x. So this is just going to be 2 times the thing that I had. So whatever I'm taking the derivative with respect to. Here was with respect to x, here with respect to a, here's with respect to sine of x. So it's going to be 2 times sine of x. Now, so the chain rule tells us that this derivative is going to be the derivative of our whole function with respect, or the derivative of this outer function, x squared, the derivative of x squared, the derivative of this outer function with respect to sine of x. So that's going to be 2 sine of x, 2 sine of x. So we could view it as the derivative of the outer function with respect to the inner, 2 sine of x. We could just treat sine of x like it's kind of an x, and it would have been just 2x, but instead it's a sine of x. So we say 2 sine of x times the derivative, let me do this in green, times the derivative of sine of x with respect to x, times the derivative of sine of x with respect to x. Well, that's more straightforward, a little bit more intuitive. The derivative of sine of x with respect to x, we've seen multiple times, is cosine of x. So times cosine of x. And so there we've applied the chain rule. It was the derivative of the outer function with respect to the inner. So derivative of sine of x squared with respect to sine of x is 2 sine of x. And then we multiply that times the derivative of sine of x with respect to x. So let me make it clear. This right over here is the derivative. We're taking the derivative of sine of x squared. So let me make it clear. That's what we're taking the derivative of with respect to sine of x, with respect to sine of x, and then we're multiplying that times the derivative of sine of x, the derivative of sine of x with respect to x. And this is where it might start making a little bit of intuition. You can't really treat these differentials, this d whatever, this dx, this d sine of x, as a number, and you really can't. The notation makes it look like a fraction because intuitively that's what we're doing. But if you were to treat them like fractions, then you could think about canceling that and that. And once again, this isn't a rigorous thing to do, but it can help with the intuition. And then what you're left with is the derivative of this whole sine of x squared with respect to x. So you're left with the derivative of essentially our original function, sine of x squared with respect to x, which is exactly what dh dx is. This right over here is our original function h. That's our original function h. So it might seem a little bit daunting now. What I'll do in the next video is another several examples, and then we'll try to abstract this a little bit.
All right. So, yeah, nice. Yeah. It's gonna be kind of weird to have video within a video, but whatever. I'm probably gonna get plagiarized. I'm gonna get booted off YouTube.
That's better.
So I've been told apparently this is bad form, but this is the way
That was so confusing.
Really?
Yeah.
All right. Well, I'm going to elaborate. So. Hold up. All right. So basically, if I have a function, h of x, let's say. So, guys, I'm going to elaborate on this. So, if I have a function e to the 4x, there's a function within a function, right? The function within e to the 4x is 4x. So, I could say, oh, that's like another function, ux, which is 4x. You with me so far?
Yeah.
Yes? Okay. So I'm going to first, so to find, I want to find dh dx. But in order to do that, well, a little trick I could do is first I'll take the derivative of h with respect to u, and then I can multiply it by the derivative of u with respect to x. So the way I like looking at this is that it's I like the way that he explains that. It's basically like canceling those things out. I've been told apparently though that's bad form. So whatevs. I kind of get like it kind of makes me think about like the difference between physics and math, where you know, if you got something like an asymptote or something, you know, a mathematician will say like, oh, it gets really close to that. To you know, whatever number or whatever, or a physicist goes like, it's basically that number, come on, whatever, it's fine. You know, where yeah, math is more, yeah. Okay, so but yeah, that's the way I like to look at it. So first I can do this. I'm going to take the derivative with respect to u. Well, what's the derivative of, so if I did that, took the derivative with respect to u, so that'd be like, if I had h as a function of u, that's e to the u. What's the derivative of e to the u? E to the u. But u is just 4x, so that would be e to the 4x. Whoa! Whoa! What are you doing? So e to the 4x. And I can do the same thing over here. I'm going to find out this part. So that's this part right here. I'm going to find this part, which is du dx. Du, what's the derivative? What's the derivative of 4x? 4. With respect to x, yeah, it's just 4. So I'm going to take that, and just like this, I got dh du, which is this. And I'm going to multiply it by du dx, which is 4. So I get dh dx is just going to be 4 e to the 4x. Yo.
So basically, you're keeping your original inner function with the first one. So e to the u, it's still 4x. It wouldn't change.
Yeah, basically, if I find a function within a function, you're going to see. I'm going to like, this is the way I like to look at this chain rule. But now we're going to kind of develop a shortcut. Like, once you do a number of these, it starts to make a little more sense. Like, just like integrals or derivatives, it's the, again, I'm not going to get too much into the theory of it. I'm just going to cut to the shortcut. So let's say I have a function sine of 3x squared. If I had just sine of x, I could just take the derivative of that and I'm done. But there's the function 3x squared inside of sine of the sine function. So the way I like to work is outside in. So first, I'm just going to ignore the function within the function. I'm going to go outside. What's the derivative of sine of anything?
Cosine.
So I do cosine, and I leave what's inside alone. But now I got to multiply by the derivative of the inside. What's the derivative of the inside? 6x. So that goes to 6x cosine 3x squared.
That's really.
All right. So, and now I'm just going to pull some problems out of here. So let's see. Let's do let's do the square root right here. Or yeah, square root of 2x minus 9. So we're going to do the square root. So we got a function. What do they call the functions? Doesn't really matter, but g of x. So g of x is the square root of 2x minus 9. So I got one function, which is like the square root of something, but then it's, I'm sorry, I got one function, 2x minus 9, inside another function, which is the square root of something. So I have to apply the chain rule. We want to rewrite this in a better form, so that would be 2x minus 9 to the 1/2 power. Now that's going to be easier to do. So how do I take this derivative? I go outside in. What's the derivative of anything to the 1/2 power? I take the 1/2 and drop it down. So the derivative of this is going to be 1/2. And then I'm going to keep what's inside first. And then the 1/2 power becomes a negative 1/2 power. And now I want to take the derivative of the inside. What's the derivative of 2x minus 9?
2.
2. So I'm going to multiply that by 2. And yeah, it'll cancel out with that. So I get dg dx is 2x minus 9 to the negative 1/2 power. Trust me, with a little practice, this starts making sense. Oh, okay. Let's see. Let's do natural log. Natural log x to the 4th. So we got natural log of x to the 4th. So again, I got a function, natural log, a function x to the 4th within a function which is natural log. So I have to apply the chain rule here. So the derivative of this df dx is, what's the derivative of natural log of anything? 1 over that thing. And then I'm going to multiply it by the derivative of the inside. What's the derivative of x to the 4th?
4x cubed.
4x cubed, right? So and so you can see those will cancel like that, and I'll get my answer, which is 4 over x. So that's the derivative of natural log using the chain rule. Here we go. Let's get crazy. Oh. Yeah, let's do this one. Y equals negative x squared plus 6x minus 4 to the 5th power. So the derivative of this. So I got a function in here, but there's another, it's with another function. So, got to do the chain rule. So what's the derivative of anything to the 5th power? 5 of that thing. And good, to the 4th. Because I subtract 1. But then I got to take the derivative of the inside. What's the derivative of?
X plus 6.
So I got to multiply this by negative 2x plus 6. Yeah.
You missed the 4 to the 4th power.
Thank you. So you're going to get more practice with this on this activity we're going to do today. Questions though so far? Oh, one more I want to do. I kind of like. I'm going to do the derivative, so we'll say y equals 1 over e to the x. I don't like something with 1 over that, so I like putting all, when I'm taking derivatives, I like everything in the numerator. What could I change e to this function to? E to the negative x, right? I throw it up in the numerator, I got to switch the sign. So now I'm going to take the derivative of this. Derivative of e to the x is just e to the x. So, but it'll be e to the negative x because it just stays that. But then I got to take the derivative of the inside. What's the derivative of negative x? Negative 1. Thank you. I'm getting lazy. Questions, comments, concerns here? All right. So my last big idea before I'm gonna kind of show you guys a bit of a demonstration here with this warm up. So and then we're gonna go into this activity to reinforce it. So basically, you show up and an object moves around a central point in a circular motion at constant speed. So you see some object that is moving with a constant speed in a circle. Is the object accelerating? Why or why not? So is the object accelerating? Why or why not? So people who have not taken physics, you're going to talk to the people who have taken physics and make your prediction. What do you think? Is it accelerating? Why or why not? So go ahead, try that. So make your prediction.
What's the reason why? What do you guys think? I'm gonna say yeah.
So yeah, people who've already taken physics, you don't want to spoil it because that's gonna, so just be asking questions, listen, all right. There's a lot of good reason for any of these. So but hopefully you made your prediction. So I got an eyeball here, and so this is an accelerometer. It's an accelerometer. So it works because so I'm going to move this way. I'm going to accelerate this way. Which way do you think the eyeball is going to move? So it's going to move that way. Okay. All right. So and we're looking at the initial movement because as you can see it bobs up and down a little bit. So we'll look at the initial movement. So here I go. I'm going to move to the right. So here. Try it again. I'm going to move to the right. Move to the right one more time. You look at the initial. So now I'm going to move this way. Which way do you think it's going to accelerate now? To the left. Okay, here we go. All right. Here we go. Show this. So it tells me the direction of my acceleration. So I'm going to do basically this, where I'm going to stand in the center. I'm going to have this out like this, and then I'm going to spin in a circle. Make a prediction. Where do you think it's going to point? Go. Talk. Where do you think the eyeball is going to point when I'm going to spin in a circle? Like, with me in the center. All right. So, here we go. Hopefully you've made your prediction. It's important to make your prediction. You want to identify what your model is, what you think. So, here we go. And I'm going to spin.
Whoa.
Wait,
Why are you spinning me around?
it's looking at me. All right. So go ahead, talk to each other about what you saw while I recover.
He's like balled up.
Oh, that's busy with work.
Accelerating or not? No, it's not. It's constant. Okay, lost the new. You want it back in?
Okay, so you saw what you saw. I'm not going to. I'm not going to go any further with this. We're going to reinforce this of what you saw by this activity you're going to do. So you're going to be analyzing the motion of a bee that can be explained. That's the equations of motion. So there's a, yes, please, yeah. There's a, oops, sorry, you can't see that. So there's two equations of motion. The angles are in radians. I use Google Sheets to calculate this. You're free to as well. If you have like a table function in your calculator that does it, you're free to use that as well. If you like, because, I mean, do you want to do the calculation 16 times? Probably not. Yeah. So this is position, by the way. These are positions. And when you guys go to graph the position, you're not graphing position versus time. You're graphing vertical position versus horizontal position. So this is a parametric function. The parameter is t. And we've already done this with projectiles, basically. Right? I showed you the launch projectile. You've seen in the diagrams there's y and x. You know, but then there's a parameter of time. Depending on the time, the object could be at different points, right? So that's the same idea here. So, and you're going to be taking the derivative of these, so you're going to be applying the chain rule, which is why we learned it. Yeah, so you're going to do that, and then you're going to get velocity and acceleration. A couple of things. If you're, so yeah, and you're going to spend the rest of the time working on that. So if you do use Google Sheets, you can write cos. When it gives you the option of, do you mean cosine function? Click yes, that's exactly what I mean. Click on cosine function. It needs to have parentheses before